This is Physics 2212, Lab 5, which looks at magnetic braking with Faraday's law. The purpose of this lab is to determine the effects of a solenoid on the velocity of a falling magnetic dipole, then to computationally and visually model this relationship in GlowScript. The physics concepts looked at in this lab are Faraday's law, flux, and Newton's second and third laws. The results that I found were that the actual fall time of the magnet was 1 second, whereas the computed fall time was 1.381 seconds. Magnetic flux is the amount of magnetic field passing through a surface. Flux is equal to the magnetic field normal to the surface multiplied by the area. Faraday's law says that changing magnetic fields induce current in conductors, which creates electromagnetic force. EMF is equal to the absolute value of the change in flux over change in time, which is also equal to the integral of the magnetic field multiplied by the changing area. And in this case, where there's an induced current, the EMF is equal to the current multiplied by the resistance. Newton's laws show that force is equal to mass times acceleration, and that any force will act in an equal and opposite pair with another force on two objects. For the experimental portion, I took a magnetic dipole and dropped it through a tube of tinfoil. I then video recorded the drop and marked the times of the entry and exit from the tube 5 times and took the average time that the magnet took to pass from the top to the bottom. I also measured the length and the width of the tube. GlowScript model, I first used the function for the magnetic field of a dipole that I created in Lab 3 as shown below. Then I created a new function for the change in flux over time. So the distance would be the ring's y position minus the magnet's y position at that time. And then the magnet velocity, which is updated over time, is the speed. And then I used the known flux equations to create the actual changing flux, which is shown right there with the numerator and denominator functions. Now, using that dipole definition, I was able to create a function to find the magnetic field at each ring, and all of those were added up to create the total magnetic force on the magnet as it moved through the ring. Then using that force and what we know from Newton's laws, I was able to update the bar's velocity and then use that updated velocity for each position to update the bar's position. And then I was able to create a graph of the bar's y velocity over time. And as you can see on the right, I was also able to model the current, which is shown in blue and red on the tube as the magnet passed through, and so the magnet being the system with it affecting its surroundings, which would be the tube. So experimentally, my average drop time was 1 second, and the theoretical drop time found by GlowScript was 1.381 seconds. And then the velocity versus time graph from GlowScript that was generated is on the right. So these could be different for several reasons. The dipole that I used, or the dipole moment from the Lab 3 may not necessarily be correct. That one was also created using computation. And also this one does not take into account things like air resistance or the fact that the tinfoil might not be at an exact thickness throughout the whole tube. Additional questions regarding this experiment include, what if the resistance of the solenoid or the tinfoil was reduced to near zero? So the current induced by the EMF is proportional to the resistance. A smaller resistance would induce a much larger current, which would then create a greater magnetic force, and this would further slow the magnet's descent by working against gravity. Now, if holes were cut into the solenoid or the foil tube, the total force would lessen, which would speed up its descent, because current can only flow through uninterrupted conductor loops, and those holes would interrupt the loops. So there would be less complete ring regions of the tube that would actually be able to carry a current and induce that force. Thank you.